Volume with known cross sections. Objectives. Find this lesson you should be able to determine the cross section of a given three-dimensional object. Visualize the three-dimensional object given the base of the cross section. Provide a formula for the area of the cross section with respect to x or y. Set up an integral with respect to x or y that will yield the volume of the object using correct limits of integration. So cross sections. So what is cross section? Well, first let's talk about why we need a cross section. So what we're going to start doing is we're going to start finding volumes of objects here. And to find a volume, what we're going to do is we're going to take a cross section, which is just, the best way to think about it is like a slice of the volume. It's like right here. It's a little slice of that 3D object. It's a little 2D version of it, right? The 2D version of that 3D object. So we call that a cross section. And we use that cross section to help us find the volume. So like, how do we do that? Well, if we find the area of this cross section, you can integrate that area from the length of the whole object, and we would get the volume of the whole thing. Right? You might say, like, wait, how does that work? Well, even down here, if you find the area of this guy, right? That's another slice, another cross section. We're going to go on the whole thing. The way you do it around the whole thing is by integrating it. Find the area of this one, find the area of the one behind it, find the area of that one, find the area of all of them, gets you the whole volume. So that's kind of the idea. So if you get a picture like this, right? Here's a little cross section for that pyramid. If we integrate that throughout from 0 to b, we end up getting the whole volume, because all you're doing is filling it up. So you fill up the area right there, area right there, area right there, right there, right there. You get the volume of the whole thing. Same thing with this one. If you follow, here's a little triangular cross section, right? If we integrate that guy, integrate the area from negative r to r, what we can do is get the area of every little slice here. And when you add them all up, which is what integration is, right? So it's a summation of all this stuff, you'll get the full volume. So like, here's some artist renderings of it. You can see like all the little slices. There's infinitely many slices. Just like if you just add up, when we integrate, so when you find the area, you find the area of one of these. And then when you integrate, you're adding up all of them put together. And that's what gets you the volume. So that's kind of the idea. So volume with no cross section. So suppose you have a solid body extends from A to B. Let A of x be the area of the vertical cross section at x, and then the volume of the solid is given by the volume is given by the integral from A to B of the area A of x. So that's what I want you to know. If it's a cross section, so if it's a volume, I should say, of a known cross section, the way you find that volume, you just integrate the area formula. That's it. So a lot of times we write that as the volume equals the integral of A of x from whatever the limits are. So that's volume of cross section. Volume of cross section is you find the area of one of those cross sections, integrate it from your limits, and then you kind of fill up the whole thing. So you find the area of that one, you'll eventually find the area of that one, and that one, and that one, and these. It'll fill up the whole thing to get you the volume. Right, same thing happens here. You find the area of this little cross section right there. You integrate that little area from 0 to whatever this guy is, and it fills up the whole thing, and you get your volume. So that's the key here, right? Volume is this volume no cross section. You just, to find the volume of something, you just find the area of the one cross section, and then you fill it up from the whole interval. So we're going to skip past the top of the y-axis in a little bit, but first let's do an example. The base of a solid is bounded by y equals x squared and y equals 1. Sketch the region and find the volume of the solid for each of the following cross sections taken perpendicular to the x-axis. So first let's just draw this. So y equals x squared. Let's draw a sketch, something special. Something like that, and something like that. Y equals 1. For the sake of, so we can see a little better, I'm going to make 1 up here. So you just kind of see it. Like that. So this is a section we're looking for. We're looking for this section. We didn't find the y-intercepts. Sorry, the intersection points. And the way we find actions, the same as we always do. If we want to find the intersection, we just set the two equations equal to each other. And we solve. I get x equals plus and minus 1. So here's negative 1, and then here is positive 1. So those are our limits. And here's the section, right? So here's the thing we're trying to find the volume of this. So what happens is, we know the formula. So for every single one of these, I know the formula is going to be integrate -1 of 1 of my area function, dx. Alright, so for every single one of these, all we have to do is figure out what the area function is, then integrate from -1 to 1. That is it. Now, area function changes. It depends on the picture. So our first one to do is equilateral triangle. So let's draw a picture of it. Let me draw one down here so I can play with it a little bit more. So first we're going to do equilateral triangles. So equilateral triangle kind of looks like this. Remember, it's smaller the closer to the beginning. It just follows the length of the function. Remember, the idea is there's infinitely many of these. Every single like slice, there's all the way up. But that's kind of the idea. So if I drew it up here, it looks like this. Equilateral triangle. Kind of like that. Again, the whole idea is that they fill up the whole thing of equilateral triangles. And what we want to do is find the area of one of these guys. If we can find the area of one of these guys and then integrate it across the whole length of it, we'll find the volume. So all you're going to do is out of all the infinite areas. So to do that, we need the area of an equilateral triangle. Now, I don't expect you to know this right now, but as of today, you should. Area of an equilateral triangle is radical 3 over 4 s squared. So this is rad 3 over 4 s squared. That's my form for equilateral triangle. Rad 3 over 4 s squared. Remember, it's rad 3 is on top. It's rad 3, not rad 4, because if it was rad 4, it would just be 2. So it's rad 3 over 4. So if I was doing A here, again, this is the form for all these problems. We're going to get from -1 to 1 of my area form, which happens to be this guy. So rad 3 over 4 s squared dx. So that's the main part of it. But we're not done. I can't just leave it s. That has to tie to my equation. This s here is the length of your function. Is this guy right there. That's what s is. S is this guy or this guy. S is your function. And my function here is just top minus bottom. So this is my s. That's always just top minus bottom. In this case, our equation for top minus bottom is 1 minus x squared. So my s is going to be 1 minus x squared. Right, because that's the length. That's all that is. What's s? S is the function. How long is our function? Our function is this long. It's the top minus the bottom. Even here, right, it's still the top minus the bottom. Even there, top minus bottom. So my s here turns into top minus bottom. So my equation is this. Plug in s, so 1 minus x squared, squared dx. Right, that squared is from the s. So I plug it in for this, it happens to be like that, and that would be my answer. Now again, I'm just focusing on how you set it up. This we can plug into our calculator, no problem. Right, the key is how you set it up, and that's the most important part here. The way you set it up is, if we're doing volume of known cross section, is always, I see those words, I think, integrate the area formula. So we're going to integrate the area formula. What's my area formula? In this case, the picture is equilateral triangles. So here's my equilateral triangles. So the formula for equilateral triangle is this. So I'm integrating that formula. All I gotta do is find out what s is. S is the length right here. And in this case, it's top minus bottom. So it's 1 minus x squared. Well, in this case, it's 1 minus x squared. So I plug it in and I get my answer. And that's how you do equilateral triangles. Now let's do squares. So square changes the picture. So for squares, we show on the side of a square, right? If I draw a square here, length times equals width, so it's kind of like this. And again, it goes throughout the whole graph. If I had a small one, it look like this. It's just however big the thing is, that's my square. It rolls out the whole picture, so it's bigger, like that. So that's a square. And the length in the area of a square is just base times height, but where base equals height, so base squared. Also known as side squared. So that's my formula for squares, just s squared. So if I'm plugging into my equation here, we're going to integrate from -1 to 1 of s squared dx. Right, it's a different formula because it's a different picture. We're doing squares. Area of a square is side squared. What's my s? Well, the same thing it was last time. S doesn't change. S is the length right there. S is just top minus bottom. So s is going to be 1 minus x squared. So that's what I'm going to plug in for my equation right here. We're going to integrate from -1 to 1 of s, which is 1 minus x squared, squared, because that's this part, dx. And that's the area of, that's how you do volume with the square. We found the area of this one square right here. and we fill it up the whole way. So that's squares. Now let's do rectangles. Rectangles. So let's draw a picture of a rectangle. Rectangle kind of looks like this. It doesn't have to look like this, so it can be a little longer. Well, it has to be like that. Again, there's way more than I'm drawing. It just goes out for the whole graph. I can't draw all of them. So this will give an example. A rectangle looks like this. And goes down to get a picture of it. Every rectangle, length times width or base times height. And here's the thing about a rectangle. So if I did my formula right here, -101 of base times height. We can't have two variables. We only have one thing. We have an s we can fill out. That's going to be one of them. It can't be both of them. So in rectangles, they have to tell you something about the height or the base. In this case, it tells us the height is 2. So my formula is actually now this, because I know the height's 2. All I gotta do is find my base here. Also knows my side. The base is just the length right here. It's just s. But for rectangles, they have to tell you something. It doesn't always have to be like, oh, its height's 3. It could say like the height is 3 times the base. There has to be something though. They have to give you something about the height. So this is my formula, right? Base times height. The my height's 2, so this is my formula. All I gotta find now is s. Well, s is always the same thing, right? It's the length here, or in this case, sorry, my base, which is essentially the s. It's the length here. So we use that to find the area. So we just plug it in. So if I want to find my volume, this is an integral from -1 of the area formula. Area formula is base times height, but now I know my base, or my s, is 1 minus x squared, and then my height is 2. And that is it. If I do that, I'll find the area of each one of these, and then you integrate across the whole thing, you get the whole volume. That's all it is for this stuff. It's just literally take the integral of the area formula. If you know what the side is, then you can fill out your area formula and you're done. So that's rectangles. Now we're going to move on to semicircles. Semicircles. The area of a semicircle, which is half a circle. So let me draw it first. So it's half a circle. If I draw one up here, it's like this. Half a circle. Again, you keep on going. Something to that effect. Now, every semicircle is half a circle, so it's 1/2 base times pi r squared, sorry. So if I was using this formula, it's just integral from -101, 1/2 pi r squared dx. Now, the thing is, what is our r? So we know what s is. S is this guy right here. S is at full length. The thing is, though, we're talking about a radius of a circle. Radius of a circle is not that full length. That's the diameter. So the r is actually only going to be half of our radius. Half of our s, sorry. So for a semicircle, radius is equal to 1/2 s. So if I was to do this equation right here, remember s doesn't change. It's still top minus bottom. I'm going to do 1/2 of 1 minus x squared. That'll be my radius. So that's what I got to plug into here. So this equation would be -101 of 1/2 pi r squared. My r, though, is just half of the s because s is the whole length, radius only goes halfway. That's what makes this one funky. And that would be my area. So again, I like this one my calculator, but that's the way you set it up. Again, so semicircle is a little funky because the radius in your formula, you normally just plug s in, but the radius for a semicircle is only half of the thing. The way you draw it, you draw a semicircle the whole way down, so you get the diameter is the whole s. So radius is only halfway. If you think that's funky by itself, wait till we compare it to quarter circles. So I'm going to erase everything, but I'm going to leave a couple of the semicircles up so you can see the difference. Quarter circles, so that's 1/4 of a circle. So let's draw the picture for that. So a quarter circle is only 1/4 of a circle, so it's going to look like this. Kind of like a shark fin. So quarter circles are drawn differently. They kind of look like 1/4 of a circle. So it's 1/4 pi r squared. And why is that such a big deal? Because it changes with the s and the r are. So -101, area formula is 1/4 pi r squared. But look at this one, right? My r happens to be the s because the way it's drawn, r equals s. So I don't have to divide it by 2 because the radius happens to be the way it's drawn, happens to be the side length. So s never changes. So, well, it never changes in the problem, this problem. So this will be my formula. Right, so I say semicircles is the funkiest one. Semicircles is where the radius is only actually half of the side, because the side is the full diameter. In a quarter circle, the radius is the side. For almost all of these, the S is the thing you kind of plug in. So that's a general idea. But I cannot stress how much I want you to understand that. But it says volume of a known cross section. They're not as hard as it sounds. You already know the formula. It's going to be the volume is going to equal the integral of my limits of the area formula. You know the area formula, your sets, you have to know the area formula. So if they say circle, you have to plug that down. Well, it's not going to be a circle, but semicircle, you have to plug this or this. Equilateral, isosceles, they could easily say isosceles, it's a different formula. Square, rectangle. If it's a rectangle, I can give you one of the sides. But you draw the picture, you know what they're talking about, then you find your S or your R, your whatever. Right? It's always like top minus bottom. But that's what we do these problems. We integrate the area formula. So this is with respect to the x-axis, like these were all up and down perpendicular ones. Let's talk about how you do it with respect to the y-axis. So volume of a no cross-section perpendicular to the y-axis. Suppose that y solid extended to y equals c, y equals z, let y be the area of the known cross-section. So you can see here, this is my cross-section. And we're going to pull it up and down. We're going to go vertically. So here's the thing about this one. When we do these, it's the same idea, a to b of the area formula. Only difference is now a and b have to be with respect to the y-axis. So if I was doing this one here, let's say this is 0 and this is 12 or whatever, it's respect to the y-axis. And then also, what's the biggest difference? When we do top minus bottom, there's no more top minus bottom. Since we're going left to right to fill out our integral, we go right minus left. Other than that, it's the same thing. But like, other than that, it's the same thing. So if they give me a problem like this one, where, oh, here's my area formula, that makes it easy. Because I just integrate from my limits, 0 to 2, of my area formula, which happens to be pi 4 minus y squared dy. Because remember, they have all the limits have to match. All the variables have to match. So that's all you do. If they give you the area formula, you just plug it in. It's super easy. There's nothing easier than a volume of known cross section when they give you the area formula. They just give it to you. It's more difficult when you have to think of the area formula yourself, or you have to find the limits yourself. So, but that's easy. When you have to find your own limits, you have to set your own equation up, find your limits, right minus left. Let's do a couple examples. The base of a solid is bounded by y equals x cubed, and y equals 0, and x equals 1. Sketch the region and find the volume of the solid based on the following cross sections taken perpendicular to the y-axis. So y equals x cubed, that's a cubic graph, so it looks kind of like this. Then we have x, y equals 0, that's just the x-axis. That's this line. And then x equals 1, so let's just draw a picture like that. So this is my region. So we're starting at 0, you go to 1. I do need to figure out what this point is right there. Now easy enough, I have y equals x cubed and I have x is 1, so I know what the x is, so you just plug it in. Y equals x cubed, or 1 cubed, so just 1. So that point is 1 and 1. So there's my region. We're going across the y, we're going perpendicular to the y-axis, so we're going to draw our pictures up and down, we're left to right. So that's all that means. Y-axis is horizontal. And that's it. So let's do the first one. Let's do equilateral triangles. First key to this is know our formula. So for equilateral triangle, it's radical 3 over 4 s squared. Next key is to draw it correctly. So if you want to picture what's going on. So we're drawing it like this, right? So we're going horizontal, perpendicular to the x-axis, y-axis, sorry. Perpendicular means like, right, makes a right angle with the right axis. You're going parallel to the x-axis. So those are our pictures. So we know the formula. We're going to integrate. Now here's the thing. We're going this way, up and down. So we're going from 0 to 1 of our area formula, dy with respect to y. So again, up and down because it's with respect to the y-axis, perpendicular to the y-axis. So we're going up and down. So we're going from 0, x-axis, to 1. And then our area formula. So now we need to find the area formula. Again, area formula is this guy, so it's 0 to 1 of rad 3 over 4 s squared dy. Only thing left is to find our S. Well, S never changes. S is still the same idea. It's this guy right there. That's our S. But what's the formula for that? So as I said earlier, we're going to do right minus left. So in this case, my right side is x equals 1. Now my left side, here's a lot of people make a mistake. A lot of people put x cubed. We can't do this. Notice it's all with respect to y. Even this is with respect to y. This is x equals 1, not y equals 1. So this is all with respect to y. So the trick here is just solve for x. You want y in the equation. So I'm going to get my equation here. I'm just going to solve for x. Take the cube root of both sides. And I get x equals cube root of y. That's my equation. That is my s. So my s here in this formula is going to be integral from 0 to 1 of rad 3 over 4. S is 1 minus cube root of y squared dy. And that's the formula. Now again, keep in mind a couple of things, right? We're doing volume of known cross section, so we just integrate the area formula. What's the area formula? Well, our picture right now is equilateral triangles, so we're going to use this formula. Let's plug it in. Now all we got to do is find what x is. Sorry, what s is. Remember, we're doing horizontal. We're going with respect to the y, perpendicular to the y-axis, so it's going left to right. So we just go right minus left, like top minus bottom, but right minus left. So the right side is 1 minus the left side, which is this equation. But you can't use x cubed. We need it in terms of y, right? Everything here is with respect to y. So you got to solve for x. So cube root both sides, we get this. And that's our equation. So that's equilateral triangle. Now let's do squares. For squares, right, the formula is s squared. Knowing the formula is make your life a lot easier. So I already have this part down. It's going to be the integral from 0 to 1 of my formula s squared dy. All I got to find is my s. Well, my s hasn't changed. Now we're drawing squares. A little bitty square. But my s is still this guy, which is still this guy. So my formula is just going to be the integral from 0 to 1 of 1 minus cube root of y squared dy. Again, all we're doing is plugging our s, our length here, how long is the side, this function, into the area formula, which is right here, s squared. So we get that, and that is it. Right? A lot easier if you know the formulas. So that's it for B. Now let's do C. I'll just add on to it right here. So if I was doing C, so it's still the same area, 0 to 1, area formula, dy. But now we're doing rectangles. So the area changes. It's 1 base times height, dy. Again, they have to give you something about the area of the base. In this case, they tell you the height is 2 again. So that's the easiest one, where they just tell you the height straight out 2. So my formula becomes this, 0 to 1 of base times 2 dy. All I need is my base. In a rectangle, the base is the same thing as the s. Drawing real rectangles. So my s, my base, is just 1 minus cube root of y. So my formula here is going to be 0 to 1 of 1 minus cube root of y times 2 dy. And that's it for area of a rectangle. So only 2 more left. Semicircles and circles. So I'm going to erase this and do all those. Semicircles. Remember, semicircle is half a circle. So my formula is 1/2 pi r squared. Now, especially with semicircles, and quarter circle, it's super important to draw it. So I'm going to draw it. So semicircle looks like that. We're doing a little half a circle. Something to that effect. So my area, this is 0 to 1 of my area formula, 1/2 pi r squared dy, right, in respect to y. Now again, my r in this case, that's my semicircle. It's this guy right here. But this is the diameter. So this is a special one where your r is actually this 1/2 of the s formula. My s formula is all of this. So my formula is going to be 0 to 1 of 1/2 pi 1/2 s. S is 1 minus cube root of y squared dy. So we get all of that for my semicircle, right? Semicircle is the worst one, by far. So that's semicircles. And then we'll finish this off. The last one, we're going to do a quarter circle. Tricky quarter circle is 1/4 of a circle. So 1/4 pi r squared. Again, it helps if you draw the picture. So a quarter circle, it's a little different. The radius is the length. You're drawing little quarter circle, little shark fins. Something like that. So the formula for the volume is this. integral 1 of 0 to 1 of the area formula, which in this case is integral from 0 to 1 of 1/4 pi r squared. But in this case, the s is the exact same thing as the r. The radius is the length of the side. So my formula is just going to be integral from 0 to 1 of 1/4 pi s squared, so 1 minus cube root of y squared dy. And that is it. And that's, I always do that. That is the volume of known cross section, right? The general idea is just this, right? The whole general idea of this whole section is you would just integrate from A to B of our area formula if we're doing cross sections, right? So you have to know your area formulas, right? There's all the different ways. If it's a circle or semicircle, you have to know those formulas. But all we're doing is we're integrating the area formula. And your s is just how long is it? What's the distance between those two equations? That's all it is. Either top minus bottom, either top minus bottom or left or right minus left, and that's it.